now we're going to move into, we're going to at least prepare for doing the integration by trigonometric substitution. Now these types, this is unfortunately one of the more difficult topics of the semester. In fact, probably if we were to rank difficult topics this semester, I mean, all of it is really, none of it's really easy, but unfortunately this topic is sort of near the top of level of difficulty. And then once we get to the very end of the semester, we might be rivaling that for a level of difficulty. But anyway, from here on out, it's probably going to get a little bit easier maybe. But anyway, let's take a look. Before we do integration by trig substitution, though, we have to have a section that even just prepares us to talk about that topic. And so that's what 7.2 is. It's just to prepare us for integration by trigonometric substitution. And so what we have here is just various types of trigonometric integrals. Trig integrals just in general. Which these are, you know, just in their own right important as well to be able to do integrals like this. And so what we do, in fact, if you guys have your books or, you know, have access to them fairly easily right now, you might want to just take a look. I refer to some guidelines about how to deal with these types of integrals. And they're in the book if you want to take a look at them, but they're kind of long, so I didn't want to reprint them here because it would take up a lot of paper. So anyway, if you want to look at them, they're in the book. What those guidelines are basically saying is kind of what we're going to do as we go through these anyway, but it's kind of useful to at least maybe have them in front of you so you can see what they are. It basically just deals with, like, what do you do when you have various powers of these trig functions, sines and cosines. And really what we're going to see on this section is that a lot of these integrals have sines sort of combined with cosines, and some other ones are going to have secants combined with tangents. Now why? Why do we focus on the ones where sines and cosines are combined together, or that secants and tangents are combined together? Well, because sines and cosines have the nice property that they are derivatives of each other, right? Or at least they are multiples of derivatives of each other. So in other words, the derivative of sine is cosine, the derivative of cosine is negative sine. And the same thing kind of happens with secants and tangents, right? When you take the derivative of the secant function, a tangent shows up in there, right? You get a secant tangent. When you take the derivative of the tangent function, a secant shows up. In fact, secant squared shows up, right? And so that's why these kind of go well together, because they have the other's derivative as part of, well, one function has the other function as its derivative, or at least a multiple of it. All right, so let's take a look at how this works. If you were to look at those guidelines, what it would say is, suppose you have products of sine and cosine raised to various powers, like we have here, right? Sines to the second power, cosines to the fifth power. Now what really matters is whether these are even or odd. That's the thing here. These numbers, that's what we're concerned with. Are they both even? Are they both odd? Or is one even and one odd? That really matters a lot for how we're going to proceed. And so that's how those guidelines sort of direct you. This is what you do if you have one of them being even and the other being odd. This is what you do if both of them are even. This is what you do if both of them are odd. Okay. So in this case, we're noticing that the cosine has the odd power on it, the fifth power. Now, what we're going to do here is we're going to make pretty heavy use of those trigonometric identities, in particular the Pythagorean identities and the ones at the top of the page that you see there, the power reducing identities. Okay, those are the ones we really need to make a lot of use of in this section. So in order to make use of those identities, and I'll just maybe write a couple of them up here, cosine squared x is equal to 1 minus sine squared x, right? That's a useful identity that we're going to use. Sine squared x is equal to 1 minus cosine squared x, right? These are just the Pythagorean identities. Now, in order to make use of any of these identities, what we need, or we notice, is that we have to have even powers, second powers, or even if we had a fourth power, it'd be fine because it would just be cosine squared squared. And then if that was like the fourth power, then you could just square this whole thing and it would become a fourth power also, right? So even powers really allow us to make use of these identities. If we don't have even powers, like in the fifth power there, what we'll want to do is sort of rewrite this thing so that we do have an even power on cosine. So I'm going to write it as cosine to the fourth, and then I'll just stick that extra cosine on the end there. Now, why are we going to do that? Because now we can make a very nice and easy substitution. We can say that u is equal to sine x. And if we do that, then du is going to be equal to cosine x. Now, if you look here, that cosine x dx, right? Cosine x dx, it is now right there. So what we've done is we've kind of saved one of those cosines for the substitution that we're making. And now when we see cosine x dx in our new integral, the u integral that we're going to make, we're going to have that cosine x dx turn into just simply du. So that's nice. So what does that mean? What do we do with the rest of this stuff then? Well, notice that this integral that we've rewritten here is now going to become u squared, and then there's going to be a cosine to the fourth there. But since we've made u be sine, we would probably like everything else to be a sine. That means this in particular, I would like to change that into a sine instead of a cosine. That's where the Pythagorean identities come from, okay? So what I'm going to do is say this is now sine squared. I'm going to change that to cosine squared squared. Or cosine to the fourth. Cosine squared squared. But what is cosine squared equal to? It's 1 minus sine squared, right? And then it's going to be squared again because it's cosine to the fourth. And then we'll leave that last cosine alone. So now we see, I think we've got everything that we need to just change this all into u's now. Everybody see that? So we said that u was sine x, and so sine squared is going to become u squared. And this is going to become 1 minus u squared. And then the cosine x on the end, we said that becomes just simply du. Does that make sense? How we changed this integral into u's instead of x's, using identities and rearranging things a bit. Any questions so far? Okay, good. Makes sense then, huh? All right, then how are we going to do this integral? Well, in order to do this, it's got to be written as a polynomial. So we'll go ahead and expand this as much as we can. This one has to be FOILed out, so we're going to get 1 minus 2u squared plus u to the fourth power du. Then we'll distribute that u squared. U squared minus 2u to the fourth plus u to the sixth. And then now we're in a state, or in a place where we can just do the power rule, right? We get 1/3 u cubed minus 2/5 u to the fifth plus 1/7 u to the seventh. And then last step, what was u in the first place? It was sine x, right? So now we'll just change that back. So we go 1/3 sine cubed x minus 2/5 sine to the fifth x plus 1/7 sine to the seventh x. So there we go. Got it. So these ones by themselves, they can at first look like, well, how the heck, where do you even start, right? So I hope that if you take a look at those guidelines that I'm referring to in the book, I do strongly recommend that you just take a look at them. You don't have to have them memorized, but you can kind of see the logic behind what those guidelines are suggesting that you do. There's definitely a good reason for what they're telling you to try to do there. And again, it really depends on whether you have odd versus even powers, at least on the sines and cosines. The secants and tangents work a little bit differently. So any questions on this one? Okay, and before we finish today, at the end of class, I want to kind of just talk a little bit about how that test is going to operate. I've been trying to figure out how the Respondus works, Respondus monitor, and lockdown browser. And I think I've got it to a point where I've got an idea of how we're going to make these tests run. But I just want to make sure that everybody has a webcam. You have to have a webcam to make this work, and we have to do this because this is part of academic integrity and making sure that everybody is proctored in their exams. So got to have that webcam. If you don't have one, I think the bookstore is actually ordering a bunch, so you can go and buy one. And I think, I don't know, CNM actually has some that might be able to be loaned out if anybody wants to do that, but I'll have to ask about that. But usually I think a lot of you probably have laptops anyway, and they have built-in webcams, so that should work. All right, so if there's no questions on this, we'll go ahead and clear this out of here. Okay, so next topic here. Fourth power on cosine. So in this case, we just have a cosine. There's no sines involved here, and it's just an even power. So on that last one, having that odd power was pretty nice because we were able to just save one of them, and that one sort of was useful to us when we made the substitution, right? We said that u was sine, and so that cosine showed up in the derivative. Pretty nice that worked out that way. What if you don't have that? What if it's just an even power and that's it? Well, the even powers by themselves, unfortunately, are the kind of a little bit trickier ones to deal with. And that's where these power reducing identities are going to come in. So if you have just even powers of sines and cosines, or just one by itself, you got to use these power reducing identities. So what we're going to do is write this as cosine squared, or you can even write it as cosine squared squared if you want to. It doesn't really matter. And then notice that at the very top of the page on 7.2, you have those power reducing identities. I'm going to rewrite the cosine one a little bit differently, but it's the same. I'm going to rewrite it as 1/2 plus 1/2 cosine 2x. And then there's another one of them, so there we go. That's using a power reducing identity. Okay, everybody clear on that? And then you can multiply this out, FOIL. So we're going to get 1/4 plus 1/4 plus 1/4, so that's plus 1/2 cosine 2x. And then the last term is going to be plus 1/4 cosine squared 2x. All right, now here, this is a fourth power. Unfortunately, we didn't quite succeed in getting these down to just being first powers. Now we still have that second power on that last term, right? Cosine squared 2x. So we have to do another power reduction identity on that term by itself. Okay, so then that's what this is what that will look like. So the 1/4, I'm just going to leave it alone, but then that cosine squared 2x, we have to use a power reduction identity on that one also. That's going to become 1/2 plus 1/2 cosine. Now this is actually going to become 4x now, cosine 4x. And why is that? Because if you look at the power reduction identity, right, it's I'll just look at this one right here, right? That became this, right? Well, notice that there was an x there, and when you use the formula, what happened? We doubled it right there, right? Well, the same thing is happening here, right? There's the second power. We're using the power reduction identity. Whatever was here has to be doubled in the power reduction formula. Does that make sense? So that last term becomes a 4x instead of a 2x. Okay, so now we can distribute that 1/4, simplify this as much as we can. In fact, I'm remembering from when I taught pre-calculus last time, I remember that we did this exact problem as an example, but we didn't do it as an integral, right? All we did was just say, let's use the power reducing formulas to reduce cosine to the fourth down to the point where there's only first powers of cosine. And so if this were a pre-calculus class, basically we would just say, well, we're done, or almost done anyway, once we add these constants together. But here in this class, of course, we have to also find the antiderivative. So 1/4 plus 1/8, that's going to be 3 over 8, right? So the constants can add. And let's see. Yeah, the rest of it, there's no like terms there. So we have 1/2 cosine 2x, and we have a 1/8 cosine 4x. Okay, so what that tells us then is that after all of this stuff that we've done, the integral that we started with, we've done our power reduction identities, but all of this was just equality, right? So now we're to the point where we know cosine 4x as an integral can now be done by doing this integral. Okay, now how do we do that integral? We have to use the power rule, so we're going to get 3/8 x. Now when I take the antiderivative of cosine 2x, I'm going to get 1/2 sine 2x, so this is going to become 1/4 sine 2x. When I do the antiderivative of cosine 4x, I'm going to have to divide by 4, so I'm going to get 1 over 32 sine 4x. So there we go. Okay, any questions on that one?
What is the purpose of doing 1/2 plus 1/2 cosine 2x instead of the one that was given to us?
Sorry, I didn't hear the last thing you said.
Oh, yeah. So what was the point of using the 1/2 plus 1/2 cosine 2x instead of the one that was given to us of the 1 plus cosine 2x over 2?
So that's the same thing. It's just they're the same. Like if I write 1 plus cosine 2x over 2, I mean, you could just split that up as two fractions, right? 1/2 plus cosine 2x over 2, and then that's just 1/2 cosine 2x. So, I mean, the purpose of it, I guess, for me is just I prefer to deal with binomials like that rather than if you leave it like this, it kind of gets a little messy when you multiply it by itself. Then you have to, I don't know. It's personal preference, really, for me. You don't have to do it. You could leave it as written if you wanted to.
Oh, okay. Perfect. Thank you.
Yeah, they're identical. It's just a different way of writing it. Okay, anything else on this one? So that's the antiderivative. We've found it. All right, let's see. What else do we have? So let's try some of these secants and tangents. These work, like I said, a little bit differently because with sines and cosines, it's pretty cut and dry, right? Like derivative of sine is cosine, derivative of cosine is negative sine. Those ones, pretty nice to work with, especially if you have the even versus odd powers, because if you have an odd power, you can just remove one of them, and what's left is an even power, and then you can use the identities. For these ones with secants and tangents, the derivative of let's just recall. I hope everybody does remember this, but I'll just write it anyway. The derivative of secant is secant tangent, right? And the derivative of tangent is secant squared. So we definitely need to know that. And we also need to remember our identities for the that deal with secants and tangent. So from the first Pythagorean identity, sine squared plus cosine squared equals 1, we can get one of these other ones, 1 plus, let me see, what is it going to be? 1 plus tangent squared is equal to secant squared. Is that how it works? I always have a hard time with those. but I think that's right. Is that right, Michael? For the identity?
Yeah, that identity.
Okay, good. Yeah, so that's important for us as well. And so from that identity, like if you see secant squared and you need to change it to tangents, you can change it to 1 plus tangent squared. Alternatively, if you need to change tangents into secants, you can rewrite that and say tan squared is equal to secant squared minus 1. So we're definitely going to make use of all 4 of those things for these problems with secants and tangents. So take a look at example C. We've got a combination of secants and tangents to various powers. Third power on secant, third power on tangent. Now these ones, the guidelines, honestly, I don't really remember what they recommend off the top of my head on these ones. Being even versus odd here doesn't really, it's not quite as useful. Although I guess the book probably says that it is in those guidelines. On these ones, I kind of just like think about it and try one thing. If it doesn't work, you try something else. Really, there's only 2 things we can do here. We're either going to make u be secant x and have du be tangent squared x. All right, that's one possibility. Or we're going to have u be tangent x. And if that's the case, then du is going to be secant. Oops, wait, I did that wrong, didn't I? I'm getting my derivatives confused there. Derivative of secant, secant tangent. It should be secant tangent. And then on this one, derivative of tangent is secant squared. Okay, so that's the 2 possibilities that we're going to have here. So looking at the integral that we have, which of those 2 would be better? Well, again, it might not be entirely obvious, like which one of those 2 would be better, but you can kind of just play around with it. Like what I would say is, if we were going to do option 1 here, if I'm going to make u be secant, for example, and have du be secant tangent, if I'm going to have this, then that means I'm going to need to see a secant and a tangent by themselves floating out at the end of the integral, okay? And so what you might want to do here is just say, okay, well, what happens if I do that? That means I need to take one of these secants away from that cubic and take one of these tangents away from this cubic and just write them at the end. Okay, so let's see. If I do that, that's perfectly set up to let u be secant x, right? So, but does the rest of the integral set up for that? Is this a good thing to do? So let's see. Well, if I'm going to make u be secant, then that would take care of this. That would just become u squared, right? And then all of this would become du. But what about this? That one has to turn into secants also. But since it's a second power, we've got this up here, right? We've got this that allows us to change it into something with secants. So it seems that option 1 is actually the best one to do here. I'll call that one option 2. So it looks like right away we've gotten a good option here. So what I'm going to do next is say, well, according to what we were just saying, well, we would like that other secant squared to become something with the other tangent squared to be something with secants. So let's go ahead and change it to secant squared minus 1. And then we still got this secant tangent floating out here. Now it's looking really good, because if I say from here, this is what we're sticking with, right? Option 1. We said that u is secant x. So this is going to become a new integral, u squared times u squared minus 1. And then all of that secant tangent stuff becomes simply du. So there we go. Yeah, exactly. Use the identity. Now, for this one, if we had tried option 2 first, what would have happened? Well, let's see, just to kind of look at it real quick. If we had done this instead, right, then we would have had to save 2 of the secants, right? We would have had to rewrite this so that I would have taken 2 of those secants away and stuck them on the end right there. And then that would have left me with secant to the first power and tangent to the third power. Well, both of those are odd powers, so they don't lend themselves to using these identities up here, right? Odd powers are not good for these identities. So right away, if we would have tried option 2, we would have hopefully seen, oh, well, great, we've got a odd power of secant and an odd power of tangent. Identities are not going to help us there. That's probably an indication that we should abandon that and just try the other way. So again, here, the fact that both of these are even powers, that's really what made this doable here. In particular, the tangent was an even power. That was the one that we really wanted to be an even power. Okay, anyway, back to this. Now we can do this integral, right? This is u to the 4th minus u squared. So that's 1/5 u to the 5th minus 1/3 u to the 3rd. And we said that that was, let's put the plus c, that's 1/5. What was u? Secant, right? Secant to the 5th minus 1/3 secant cubed. So there we go. All right, everybody see how that worked? And kind of what you're looking for when you're dealing with secants and tangents. And really, these are how all of these are going to work. Either u is going to be secant or it's going to be tangent. You can just kind of say, well, let's see, what happens if I make it be the first one? What happens if I make it be the second one? All right, so then with, so any questions on this one? If not, we'll go on to the next. No questions, so I'll clear this out of here. All right, so D, now remember on that, when we were talking about sines and cosines, even power of sine or cosine by itself is not that nice because we had to use the power reducing identities. Those can be a little bit messy. With tangents and secants just by themselves to an even power, maybe it's not so bad. So what we can do here is think, let's see, what if I rewrite this as tan squared times tan squared? And then I've got the identity that I can use here. Right, tan squared, what was that identity? Tan squared is equal to secant squared minus 1. And so what I can do here is change this now to be tan squared (2x) times secant squared 2x minus 1. Now, something that we need to just remember for integrals of trig functions, there's a couple out there that are just right away. We don't have easy. We don't have to really worry about anything, even substitutions. What am I talking about? If you just have an integral by itself of a sine or an integral by itself of a cosine, we know those are very simple. What other trig functions would we just like to see by themselves as an integral? Well, how about secant squared by itself? Wouldn't that be a good thing to have by itself? Well, probably, because what's the antiderivative of secant squared? That's just tangent, right? And so if we see a secant squared ever just by itself, or we can get it so that it's just by itself and just like a single integral by itself, that's useful to us. So let's see if we can maybe make use of that here. I'm not sure if we can, but let's just see what happens here. So we're going to get here, distributing that. I'm going to distribute this. Okay, so let's do these separately. In fact, let's write this. I'm going to rewrite this as tan squared 2x secant squared 2x as a single integral and then minus this integral. Okay, now looking at these separately. Again, remember that the derivative of tangent just by itself is secant squared. So seeing a secant squared is always useful, even if it's not just by itself. If you see a secant squared multiplied by any power of tangent, in fact, that's nice, because here we can just say, well, let's see, what if I make u be equal to tangent 2x? And what does that make du? Well, by the chain rule, it makes it 2 secant squared 2x. But look what we have there. There's the secant squared 2x and the dx, right? So that's nice. We don't have that 2 in front of it, so we could maybe say this is 1/2 du when we see the secant squared 2x. So now again, when we see secant squared 2x dx, we know secant squared 2x dx is going to become 1/2 du. And then what is this going to become? Well, that's what we said u was. Well, this is what we said u was, right? So u squared is what that's going to become. Circling everything. Hopefully you guys are following me. So now that integral is going to become 1/2 integral u squared du, which is, again, not bad because it's just antiderivative of that power rule. It's going to be from 1/6 u cubed. And that is then 1/6. What was u? Tan squared. So that's going to be, or sorry, u is just tangent 2x. So it's going to become tangent cubed of 2x. So that's that part of it, okay? What about the rest of it? This one. Now this one is actually easier than it might look. Whenever you have a tan squared by itself, well, that one you can just use the identity on it. Tan squared, secant squared minus 1. So we're actually going to use the identity again, and this one we're going to say it's going to become secant squared minus 1. I guess the minus has to go in front of it as well. Remember what I said about seeing a secant squared just by itself? That's very nice because the antiderivative of secant squared couldn't get much easier than that. It's just tangent, right? But since there's that 2 there, we do have to use the little substitution rule there and say that this becomes 1/2 tan 2x. And then the antiderivative of 1, again, very simple, just x. And distributing the minus sign, we get the plus x. So putting it all together, what do we get for answer? In general, 1/6 tangent cubed 2x minus 1/2 tangent 2x plus x. Let's see. Okay, any questions about that? So these, I mean, again, looking at this for the first time, it's probably kind of confusing what the heck's going on here, but you can see just we're making heavy use of the Pythagorean identities and the fact that the derivative of tangent is secant squared and the fact that the antiderivative of secant squared is just tangent. So any questions? Not. Let's do the next one. All right, so a few of these are just kind of showing like what other types of trig integrals are we going to run into. So these are kind of just outliers that you might see. What's going on here is that we have a combination of cosine with the algebraic function t, right? That t is there, sort of making this a little bit different than the other ones. So what we might want to do here is just realize, okay, let's make a substitution for that t squared. Just start out by doing a regular old substitution, u equals t squared. Oops, that shouldn't be a du on the end, that should be a dt, sorry. In fact, actually, I'm going to do a different substitution. I'm going to use x instead of u here. I'm going to make x equal t squared. And so that dx will be 2t dt. And that is going to take care of this t right here, right? Because now we see if I make this 1/2 dx is t dt, and we see over here that we've got, there's the t dt, right? Those two together are going to become 1/2 dx. And then what's going to happen to the rest of it? Well, I'll have cosine to the 5th of just x, right? So this integral will become cosine to the fifth x dx. And I guess I have to have that 1/2 there as well, right? Okay, any questions about how we got to this point? Okay, now we've got a fifth power of cosine. Well, any odd power of sines or cosines are ideal for us. They're much easier to work with than the even powers by themselves. If we have an odd power, it's set up very nicely because all we got to do is just save one of those, and then what's going to be left is going to be your even power, right? So, and then once we've got the even power on that cosine, then we can make use of our identities. Now, again, the fact that we have this cosine x dx right here is telling us that we're going to have to make u be sine x, right? Because when we make u be sine x, its derivative is cosine x dx. So that cosine x dx has to go along with the sine, meaning that the rest of the stuff that we see here has got to change into sines. That's why we're going to use the identities. We can rewrite this as 1 minus sine squared, and then square that, because really it's cosine squared squared, right? Okay, and then at this point we're ready to make our substitution. Here we can say u, that's why I decided to use x on that other one. U is equal to sine x. And so du is then cosine x. And so here we see the cosine x dx. There's the cosine x dx. We know it's just going to become du. So we're going to get 1/2. Changing this into u's now, 1 minus u squared du. Now it's a nice power function, polynomial. We can just expand that, use the power rule. We get 1 minus 2 u squared plus u to the fourth. And then for that, we can just use the power rules. We get 1/2 u minus 2/3 u cubed plus 1/5 u to the fifth. Changing all this back, we're going to have 1/2. What was u? It was sine x, right? But what was x? So we have to kind of go back to the top. What was x? X was t squared. So we're going to have a sine of u, but that's actually becomes the sine of t squared minus 1/3. That's going to be sine cubed of t squared. And then the last one, 2/5 sine to the fifth of t squared. All right, so like a double substitution on this one.
The 2/5?
Yeah, we have to distribute the 2 from the front, right? Oh, I'm sorry. You're right. It shouldn't be 2. This should be 1/10. Thank you. I was putting it in the wrong place. 1/10. Okay, any questions on that one? Okay, cool. So we have about 7 minutes or so. I think that's enough to do one more problem, do F, and then we'll save these 2 difficult ones. The last 2 are like just special cases that can't be done by any of the means that we're seeing here. In fact, this integral of the secant function has a really nice story behind it. I'll tell that story to you guys next time. But let's go ahead and do F. Okay, so what we're trying to see on this problem, so we're, again, all of these examples are sort of just designed to show you what you can expect when you deal with these types of integrals. If you do check those guidelines, what you're going to find, the guidelines from the book, what you're going to find is that the last guideline basically just says, if none of the other stuff works, then your last option, or your last hope, I guess, is to change everything into sines and cosines and then see what happens from there. Okay. So here that we have that situation here. There's no guidelines that tell you how to deal with sines and secants together, right? And so in that case, you would want to just look at the very last guideline and say, okay, well, I don't have anything that tells me what to do with sines and secants, so I'm just going to change it all into sines and cosines. See what happens. So if I do that, secant to the fifth is the same as 1 over cosine to the fifth. So that's going to give us this integral, sine in the numerator, cosine to the fifth in the denominator. Well, right away, this one's actually pretty nice because, well, look, we've got this sine x dx by itself on the top. And what's the derivative of cosine? Well, it's negative sine. So this is really set up very nicely for just a straight up substitution. Here we can just say u is equal to cosine x. And so the derivative is going to be negative sine x. And then since there is no negative over here in the integral, we'll go ahead and just move that negative to the other side here. And so when I see sine x dx in the integral over here, I see this sine x dx, I know what it's going to change into. It's going to change into negative du. So in our new integral with u's, we're going to get negative integral du over u to the fifth power, which is again pretty nice because that's just a power function. If you rewrite it like this, right, u to the minus 5, and then antiderivative of that is going to be negative 1/4, but it'll cancel with the other negative, u to the minus 4th. And then based on our substitution, that's 1/4, what was u, cosine x to the minus 4 power. Well, minus 4 power is better done with positive power like this. We can write it as 1 over 4 times the cosine to the 4th. But then that is better done with not having any trig function in the denominator and just writing it as secant to the 4th. So there we go. 1/4 secant to the 4th. All right, if there's nothing else, let's continue with the calculus stuff. So I think I told you last time that these last two here are just sort of exceptions to all of that stuff that we had done with the guidelines for doing trig integrals, right? There was all that set of guidelines in the book that I told you guys to maybe have a look at. These two in parts G and H just totally do not follow any of those, and so these are exceptions, like special integrals, I guess, that you have to know what they are, but they are not done anything like the ones that we had done previously in this section. Okay, so the secant one in particular it's an interesting integral in that it actually has some nice historical context to it. I'll just say a little bit about that because it is pretty interesting. And this occurred back in the what was that, the 14 and 1500s, I think, is when they were doing this, when they were worrying about this. So it's actually a very difficult integral to do, but once we know the trick on how it works, it's actually, it works pretty well. But people had a hard time figuring out what that trick was. In fact, I think it took like 100 years before anybody could actually figure this out. And the reason it was very important, like I said, it did have some historical context to it. And that context was, back then in the 14 and 1500s, people really needed to figure out how to make very accurate maps, right? Because what were they doing back in the 14 and 1500s? They were like sailing around the globe, right? And so to make an accurate map, what we have, a globe, of course, is the most accurate map that you can get because it's the exact shape of the Earth, right? On a globe, what you have is these lines of latitude, right? And they're all nice and evenly spaced. And then you've got this one right in the middle, that's the equator. A little bit of a history lesson here for you guys. And what the trick was to try to get an accurate representation of the globe, but on a flat surface, right? And so that posed a bunch of challenges. How do you accurately represent the globe on a flat surface, right? And so one of the so-called map projections was called the Mercator projection, if you guys have heard of that before, and that puts the equator right in the middle. So this is the one that people were working on back then, like how do we accurately represent the lines of latitude? And if you've seen the Mercator projection before, you know that the lines of latitude closer to the equator are farther apart, but the further away that you get from the equator, the closer these lines get together. Yeah, you guys familiar with that? So these are lines of latitude. I guess I probably made this a little bit too big, but that's the idea. The closer that you get to the poles, then basically the closer those lines of latitude get. And so what people back then were trying to figure out was, well, how far apart do these need to be spaced, right? How far apart should these lines of latitude actually be spaced so that they will accurately represent what we see over here? And so it turns out, for reasons that I'm not going to get into here, but it turns out that in order to figure out what this spacing actually had to be, guess what people needed to know in order to do this? They needed to figure out this particular integral. That was a requirement for figuring out what those lines of latitude needed to be, how the spacing between those lines of latitude needed to be. And so they found that it was a very difficult integral to do, or to find the antiderivative for it, because really what they wanted was a definite integral. But in order to do a definite integral, you have to do an indefinite integral. And so, in fact, I think the story goes that some king back then was willing to pay a lot of money to the first mathematician or scientist that could figure this out. And it apparently took a long time. I think over 100 years before somebody actually finally got it. And so what I'm going to show you is not actually the way that the first person got it. And I believe the first person to get this correct did it in a much more difficult way than we're going to do. So the more difficult method was actually found first. But the way that we're going to do it, somebody figured out later on that actually there's an even better way to do it. And so this is the trick. This is the trick to do the secant integral. And you can probably see why it took people kind of a long time to do this, because you would say, well, why on earth would you want to do this? Multiply by secant plus tangent over secant plus tangent. Why would you do that? But anyway, that's the trick, as we can see why in just a second here. This is why it works. Because when you distribute that numerator, you get this. Right, so that's what you get after you do the multiplication for that. Now, why does that make things better? Because if you notice now what happens, you can actually make a nice u substitution now. You can say that let's let u be the denominator of this thing, secant plus tangent. And then if you do that, that means that the derivative du is going to be secant tangent, right? The derivative of secant is secant tangent. And then the derivative of tangent is secant squared. And look where that is. That is in fact exactly what is in the numerator, right? Reversed, but it's the same thing since it's addition. Secant tangent plus secant squared. That is in fact the entire numerator. And so when you see all this numerator here, the dx and everything, we know that all of that is going to become simply du. And the numerator, since we said that was, the denominator, that was the u right there. The denominator is simply going to be u. So with all of this integral now becomes what? It's just du for the numerator and u for the denominator. Nice and simple, right? And then if we remember what that is, what is the antiderivative of du over u? That's just the natural log of u. Right? And so then we just replace the u back with what it was. What did we say u was? Secant plus tangent, right? Secant plus tangent. And that's it. So there's our antiderivative for the secant function. And so that, actually figuring that out, helped people to not get lost in the ocean, interestingly enough, back in the 1500s. So any questions? Good. I'm going to get rid of this then, and we'll try the other one. So now the secant cube, this is another exception to all of those little guidelines that we saw. How do you find the integral of the secant cubed function? So that one is another, in fact, even more difficult, I think, than the secant by itself. This one, again, doesn't follow any of those little guidelines that they give you. So what do? Well, this one actually has to be done by parts. And so this is the way we would rewrite it to do it by parts. Okay, so if you write it like that, then you can decide, well, what should u be and what should dv be, right? Remember what integration by parts requires us to do. Identify the u, identify the dv. Now, one of these I think makes pretty good sense to make dv, because in order to find v, we'll have to integrate it. And so secant squared, I think, is the best choice here, because the antiderivative of secant squared is simply tangent, right? So that's a nice, easy thing for us to find v. That means that u has to be the rest of it, secant x. And in that case, then v, the antiderivative of this, secant squared, is tangent, as we just said. Okay, and then the derivative here, du for secant, is secant tangent. Okay, so there's the beginning of the integration by parts formula, and now we'll plug that in. So that means plug that into the parts formula, we get uv, so that's going to be secant tangent uv minus the integral v du. Now, if you see what v and du have when you put them together, you get, there's a tangent here, right? There's one tangent there, and there's another tangent there. One of the tangents comes from the v, the other comes from the du. So we're going to get a tangent squared in our new integral. So we'll get tangent squared. Actually, let me write the secant first. Secant and then tangent squared. Okay, any questions so far? And now the question becomes, okay, well, how do you do the integral of secant tangent squared? So you can kind of see why this one is going to be pretty difficult, because how do you do that? Secant tangent squared is an integral. This is another one that doesn't really fit into any of the guidelines. No matter what you try to do here, it's not going to really, nothing is going to work except this. This is what you have to do from here. You got to change that tangent squared back into secants using an identity. Right? And so what was the identity for that? 1 plus tangent squared is equal to secant squared. So tangent squared is equal to secant squared minus 1. So secant squared minus 1. Okay, then we got to distribute that secant in there. So we're going to get secant, this stays, and distribute that. And we get secant cubed minus, actually I'm going to write that as a separate integral. That's actually going to end up being plus integral secant. And that's a plus again because of this, that minus there and that minus there will change into the plus. Okay, so far. Now, remember when I told you that one interesting thing that we saw about integration by parts, that there's a couple integrals where you have to use that technique where you see the integral that you're trying to solve for show up again in the work that you do for the integration by parts. So if we write secant cubed on the left there, you notice, look, there it is. There's the other secant cubed integral right there. So we can actually treat that as a variable and add that secant cubed integral to both sides. If I do that, if I add that to both sides, I'm going to have two of them on the left side. So I'm going to get the secant cubed there. And then on the other side, I'm going to get secant, still that secant tangent is kind of hanging out there. And then I still have this as well, right? The integral of the secant function. Well, that's the one we just did, right? So we don't have to do the work on that again. We already found out what that is. That's the natural log of the secant plus the tangent. Okay, and so then the final step here is to divide all this by 2, and then I'll have the integral secant cubed by itself on the left side. So secant cubed integral, divide all this stuff by 2, I'm going to get 1/2 secant tangent plus 1/2 natural log of secant plus tangent. And there we go. There's our final answer for that one. So as you can see, definitely kind of a tricky one, right? Maybe even more so than the integral of the secant by itself. Although that secant one by itself, if we didn't know what that trick was, I think it would be very difficult to figure out that that's what you have to do. But this one actually has the integral of secant as part of it, right? So I think by definition, it's got to be a little bit harder. All right, any questions on that one? So just so we're aware, for homework and stuff, right now you can just use that, the integral of the secant cubed. You don't have to actually do all the work again. All right, any questions? Okay, if not, I have 4 problems there that I'd like you to work on. In fact, actually, one of them I'm going to tell you to ignore, and that's B, problem 1B. That one's just going to take too long. It's just because you have to do like multiple power reductions, and it just takes a really long time. So just skip that one. Try to do the other ones, parts A and C and D. D is actually pretty easy. C is actually kind of hard. A, so-so. So work on those for a little bit. Okay, so there's the first one. You guys get that? Everybody got that one right. Good job. If you didn't get that right, or if you were just wondering how to begin, some things you might have wanted to notice right away. That's a third power. Remember, third powers are or odd powers are kind of nice on these because taking one of them away is usually going to take care of your substitution, right? If u is sine, that derivative du cosine is going to show up there, and that'll take care of that. And so that's nice because changing that or taking away that one cosine now leaves us with a second power there, which allows us to use this nice identity. Now everything here is in terms of sine except for that, and so that's pretty much telling us if we make u be sine, du is going to be cosine, and then everything here is going to turn into either u's or du's. And then just got power rule stuff from there. Got to write these as fractional exponents, distribute, and remember that when you distribute like that, you have to add the exponents. 2 plus 3/2 is 7/2. And then just power rule and then substitute it back in. Actually, maybe I'm remembering wrong. So it doesn't look that bad, actually. As long as you realize that you got to split it up like this. Secant squared, secant squared. So my thought process here is that that tangent's kind of stuck under the radical. I'm pretty much stuck making u be tangent x. And if I do that, then I have my secant squared right here. But if I make u be tangent, then that means everything else needs to be written in terms of tangent except for the du. And so that secant squared, we're going to have to change it into tangent. But we have a way to do that. We can use an identity. Okay, so from there we see there's the secant squared x dx. That's going to become du. All the rest of this stuff is just tangents anyway, so we'll just replace all those tangents with u's. And then for an integral like this, you would probably want to split it up as 2 different integrals. These 2 different parts of the same integral. And then just use the power rule. Well, first use the properties for exponents and then the power rule. Okay, so there we go on that one, part C. Any questions on that one? If not, I'll just do the last one. I said the last one was actually probably the easiest of these. In fact, this last one can be done either way by letting u be either secant or tangent. Make it work in either case. One of the few where that happens. But I think one of them is actually easier than the other, so let's try to do the easier one. I think you'll notice that if you do it this way, it's the easiest way. Because then you can just say u is equal to secant, du is the derivative of that, secant tangent. And you see that that's exactly what's here after we split this up, right? So all of that matches this, so it's going to change into du. And then the only other thing we have there is just secant squared, and that's what we called u, so that's just going to be u squared then. So you can see if you notice this simply becomes u squared, and the rest of it is just a du. And that's pretty simple, just power rule. Oops, what am I doing? Cubed there. So that's 1/3 secant cubed.